Which of the following statements accurately describes the affinity propagation clustering algorithm in scikit-learn? A. It is a density-based clustering algorithm that identifies clusters as regions of high density, separated by regions of low density. B. It is a hierarchical clustering algorithm that builds a hierarchy of clusters based on their distances. C. It is a centroid-based clustering algorithm that finds cluster centers and assigns data points to the nearest center. D. It is a message passing algorithm that identifies exemplars or representative data points based on the similarity between data points. E. All of the above. False. This statement describes density-based clustering algorithms like DBSCAN, not affinity propagation. Affinity propagation focuses on identifying exemplars, not density. Density-based clustering, identifying clusters of stars in a galaxy based on their density. Regions with high density of stars would indicate potential clusters. Consider a dataset of points in 2D space. A density-based algorithm would identify clusters based on the number of points within a certain radius. For example, if we define a radius of 1 unit, a cluster could be defined as a region where there are at least 5 points within that radius. False. This describes hierarchical clustering algorithms like agglomerative clustering or divisive clustering. Affinity propagation works through message passing, not hierarchical relationships. Hierarchical clustering, organizing a set of documents into a hierarchical structure based on their similarity. Documents with similar content would be grouped together at lower levels of the hierarchy. In a hierarchical clustering algorithm, the distance between clusters is often measured using linkage methods like single linkage, complete linkage, or average linkage. For example, single linkage measures the distance between two clusters as the distance between the closest points in each cluster. False. This describes centroid-based clustering algorithms like k-means. Affinity propagation uses exemplars, not cluster centers, and assigns data points based on similarity, not distance. Centroid-based clustering, grouping customers into segments based on their purchasing behavior. The cluster centers would represent the average customer in each segment. In k-means clustering, the distance between a data point and a cluster center is often measured using the Euclidean distance. The algorithm iteratively updates the cluster centers until the assignment of data points to clusters stabilizes. True. This is the accurate description of affinity propagation. It uses a message passing approach to find exemplars representative data points by iteratively updating messages based on similarity between data points. Affinity propagation. Segmenting a large social network into groups based on user interactions. Exemplars in this case would represent influential users in each group. The similarity between data points is represented by a similarity matrix, which can be calculated using different distance metrics like Euclidean distance or cosine. Similarity. Affinity propagation iteratively updates two types of messages: availability and responsibility, which reflect the likelihood of a data point being an exemplar and the likelihood of a data point being assigned to a particular exemplar, respectively. False. Since options A, B, and C are incorrect, option A is also incorrect. Only option D correctly describes affinity propagation. None. 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 D. It is a message passing algorithm that identifies exemplars or representative data points based on the similarity between data points. This function defines the affinity propagation model in scikit-learn. The parameters control various aspects of the algorithm. including the similarity metric affinity, the number of iterations to check for convergence iter, a damping factor damping to stabilize the algorithm, the maximum number of iterations max iter, a preference value for each data point preference that can be used to influence the selection of exemplars, and a random state for reproducibility random state. Python. From sklearn, cluster import affinity propagation. From sklearn, datasets import makeblobs. Create a sample dataset. X, Y makeblobs n samples 200. Centers 5. Random state 0. Create an affinity propagation model. Model affinity propagation damping 0.7. Fit the model to the data. Model, fitx. Get the cluster labels. Labels model, labels. Print the cluster labels. Print labels. Which of the following statements accurately describes agglomerative clustering in scikit-learn? A. A hierarchical clustering algorithm that begins by assigning each data point to its own cluster and then iteratively merges clusters based on their similarity. B. A centroid-based clustering algorithm that uses the mean of the data points in each cluster to represent the cluster center. C. A density-based clustering algorithm that identifies clusters based on the density of data points in different regions of the data space. D. All of the above. A. A hierarchical clustering algorithm that begins by assigning each data point to its own cluster and then iteratively merges clusters based on their similarity. True. This is the core principle of agglomerative clustering. It starts with individual data points as separate clusters and gradually combines them based on their similarity or distance. B. A centroid-based clustering algorithm that uses the mean of the data points in each cluster to represent the cluster center. True. Agglomerative clustering can be considered centroid-based in the sense that it uses the cluster's centroid average to calculate the distance between clusters. However, this is not its defining characteristic, as other algorithms like k-means are more explicitly centroid-based. C. A density-based clustering algorithm that identifies clusters based on the density of data points in different regions of the data space. True. While agglomerative clustering might indirectly consider density during the merging process, it is not a density-based clustering algorithm. Algorithms like DBSCAN are specifically designed to identify clusters based on data point density. D. All of the above. True. All the statements describe aspects of agglomerative clustering, making option D the correct answer. D. All of the above. Linkage criteria defines how the distance or similarity between clusters is calculated. Common linkage criteria include: the linkage criterion determines how the distance between clusters is calculated. It affects the shape and structure of the resulting clusters. For example, single linkage focuses on the minimum distance between points in different clusters, while complete linkage considers the maximum distance. In customer segmentation, using single linkage might lead to elongated clusters, while complete linkage might form more compact groups. This choice depends on the business objective and the desired customer profile granularity. Distance metric. The method used to calculate the distance between data points. Examples include: the distance metric defines how the similarity or dissimilarity between data points is measured. Different metrics are suitable for different types of data and applications. Euclidean distance is commonly used for numerical data, while cosine similarity is appropriate for text or vector data. When clustering documents, cosine similarity might be preferred to capture semantic similarity between words and phrases. while Euclidean distance might be more suitable for analyzing numerical features like customer purchase amounts. Dendrogram, a tree-like diagram that visually represents the hierarchical clustering process. The dendrogram is a visual representation of the hierarchical clustering process. It shows how clusters are merged at different levels of similarity, allowing you to explore the relationships between clusters and identify the optimal number of clusters. In biological data analysis, a dendrogram can reveal how genes or proteins are related based on their expression patterns. This helps understand biological pathways and identify groups of genes with similar functions. Use cases. Customer segmentation, grouping customers based on their purchasing behavior, demographics, or other characteristics. Document clustering, organizing documents into groups based on their content similarity. Image segmentation, dividing an image into regions with similar characteristics, e.g. color, texture. Biological data analysis, clustering genes or proteins based on their expression patterns or other biological characteristics. Agglomerative clustering has a wide range of applications in various fields. It's effective for grouping data points based on similarities and creating meaningful clusters. In document clustering, agglomerative clustering can be used to categorize articles, news stories, or scientific papers into themes or topics based on their content similarity, making it easier to retrieve relevant information. Code implementation. From sklearn, cluster import agglomerative clustering. Clustering agglomerative clustering N clusters 3. Affinity Euclidean. Linkage word. Clusters clustering. Fit predict data. This code snippet demonstrates how to implement agglomerative clustering in Python using sklearn. It shows the steps to create an instance of the agglomerative clustering model and fit it to the data. This code can be used to implement customer segmentation, where data represents customer data, and N clusters determines the desired number of customer segments. The resulting clusters variable will provide the cluster assignments for each customer. Which of the following statements is true regarding the Birch clustering algorithm in sklearn? A. Birch is a density-based clustering algorithm, similar to DBSCAN. B. Birch is a hierarchical clustering algorithm, building a tree-like structure of clusters. C. Birch is a centroid-based clustering algorithm, like k-means, that partitions data into clusters around centroids. D. All of the above. A. Birch is a density-based clustering algorithm, similar to DBSCAN. True. Birch incorporates density-based considerations. It uses a CF tree to capture the density of data points within clusters. The CF tree implicitly considers the density of data points during the hierarchical clustering process. B. Birch is a hierarchical clustering algorithm, building a tree-like structure of clusters. True. Birch constructs a hierarchical tree-like structure CF tree for clusters. The CF tree facilitates the organization of data points into clusters, with subclusters nested within larger clusters, forming a hierarchical structure. C. Birch is a centroid-based clustering algorithm, like k-means, that partitions data into clusters around centroids. True. Birch stores cluster centers centroids at each level of the CF tree. It leverages these centroids for efficient updates and computations, similar to centroid-based algorithms like k-means. D. All of the above. True. All the statements A, B, C are true because Birch is a hybrid algorithm, combining aspects of density-based, hierarchical, and centroid-based clustering techniques. D. All of the above. Birch CF tree A hierarchical data structure that stores data points and their cluster centers effectively, allowing for efficient updates and computations. Clustering large datasets. BERT is particularly effective for large datasets where computing distances between all data points can be computationally expensive. Pre-clustering for k-means. BERT can be used as a pre-clustering step to reduce the number of data points before running k-means, improving its efficiency. Hierarchical clustering. A clustering method that builds a tree-like structure of clusters, with subclusters nested within larger clusters. Customer segmentation. Group customers with similar buying behaviors based on their purchase history, demographics, and other relevant factors. Document clustering. Group documents with similar content based on their keywords, phrases, and semantic relationships. Centroid-based clustering. A clustering technique that partitions data into clusters around centroids, which represent the average or central point of each cluster. Image segmentation. Group pixels in an image based on their color or texture characteristics. This can be useful for tasks such as object recognition and image analysis. Anomaly detection. Identify outliers or unusual data points in a dataset by analyzing their distance from cluster centroids. Density-based clustering. A clustering approach that groups data points based on their density, identifying clusters as regions of high density separated by regions of low density. Anomaly detection. Identify outliers or unusual data points in a dataset by identifying regions of low density 1, 2, 1.5, 1.8, 5, 8, 8, 8, 1, 0.6, 9, 11. BERT can be used to cluster this data, which represents a hypothetical dataset with 6 data points in 2 dimensions. It builds a CF tree that represents the hierarchical clustering structure. The CF tree stores cluster centroids at each level, allowing for efficient updates and computations. By traversing the CF tree, you can identify clusters of different densities, which can then be used for further analysis. What is the core concept behind DBSCAN clustering algorithm? A. It groups data points based on their density, identifying clusters as areas of high density separated by low density regions. B. It partitions data points into clusters based on their distance from cluster centroids. C. It constructs a hierarchical tree-like structure representing the nested clusters. D. It assigns data points to clusters based on their similarity to predefined prototypes. A. It groups data points based on their density, identifying clusters as areas of high density separated by low density regions. This statement accurately describes DBSCAN's core concept. It identifies clusters as regions where data points are densely packed together, separated by areas with fewer data points. This is evident in the solution section, which states DBSCAN density-based spatial clustering of applications with noise operates on a principle of density, identifying clusters as regions of high data point concentration separated by areas of low density. True. B. It partitions data points into clusters based on their distance from cluster centroids. This statement describes the concept of k-means clustering, not DBSCAN. DBSCAN does not rely on cluster centroids but rather on density. False. C. It constructs a hierarchical tree-like structure representing the nested clusters. This statement describes hierarchical clustering, a different type of clustering algorithm from DBSCAN. DBSCAN does not build a hierarchical structure. False. D. It assigns data points to clusters based on their similarity to predefined prototypes. This statement describes prototype-based clustering, such as k-medoids, which uses predefined representative data points. DBSCAN does not rely on predefined prototypes. False. A. LT font style font size 14px GT LTBGT density based clustering LTBGT LT font TGT. This clustering approach identifies clusters based on the density of data points. Clusters are defined as regions with a high density of points, separated by low-density regions. DBSCAN is an example of this approach. Identifying customer segments with similar buying behavior in e-commerce high-density clusters and outlier customers low-density regions. Detecting areas of high population density in geographical data to plan urban infrastructure. Identifying clusters of galaxies in astronomical data. Finding regions of high protein concentration in biological images. LT font style font size 14px GT LTBGT core points LTBGT LT font GT. In DBSCAN, core points are data points that have at least a minimum number of other data points min-PTs within their specified radius apes. These points represent the core of a dense cluster. Identifying influential customers with a high number of connections in a social network. Finding hotspots in geographic data where many events occur within a certain radius. Detecting central nodes in a network that have high connectivity. LT font style font size 14px GT LTBGT border points LTBGT LT font GT. Border points are data points that are not core points but lie within the neighborhood of a core point ape's distance. They belong to the cluster associated with the core point, as they contribute to the cluster's density. Identifying customers who are influenced by core customer segments in marketing campaigns. Finding areas in geographic data that are connected to dense regions but have lower density themselves. Detecting nodes in a network that are connected to central nodes but have fewer connections themselves. LT font style font size 14px GT LTBGT noise points LTBGT LT font GT. Noise points are data points that are neither core points nor border points. They do not belong to any cluster and represent outliers or isolated data points. Detecting fraudulent transactions that are isolated from normal activity. Finding anomalies in sensor data that might indicate equipment malfunction. Identifying unusual patterns in medical data that might indicate a disease. LT font style font size 14px GT LTBGT EPs epsilon LTBGT LT font TGT. The radius or maximum distance within which points are considered neighbors for density determination. It's a key parameter in DBSCAN, influencing the size and shape of clusters. Adjusting the size of customer segments based on the desired level of granularity, e.g., wider radius for broader segments, tighter radius for more specific segments. Controlling the sensitivity of anomaly detection by adjusting the distance threshold for identifying outliers. Optimizing image segmentation by fine-tuning the radius to capture different levels of detail. LT font style font size 14px GT LTBGT MINPTs minimum points LTBGT LT font GT. The minimum number of points required within the ape's radius to declare a point is a core point. This parameter influences cluster density and noise identification. A higher min-PT's threshold will result in fewer core points and potentially larger clusters. Ensuring that only customer segments with a significant number of members are considered relevant. reducing the chance of false positives in anomaly detection by requiring a higher density threshold. For outlier identification, making image segmentation more robust by requiring a higher density of pixels for identifying meaningful regions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 3, 1, 5, 7, 8, 6, 9, 10, 4, 2, 3. Let's say we have a set of data points with coordinates x, y. Well, set apes radius to 2 and min pt's minimum points to 3. Using these parameters, well, analyze each point to determine its type. Point 1. 2 is a noise point, as it has less than 3 points within the radius of 2. Point 2. 3 is a border point, as it has 2 points within the radius of 2, but not 3. Point 3. 1 is a core point, as it has 3 points within the radius of 2. We continue this process for all points, ultimately identifying core points, border points, and noise points. DBSCAN will then group core points and their associated border points into clusters. This density-based approach allows for identifying clusters with irregular shapes and handling outliers effectively. What makes HDBSCAN a powerful clustering algorithm, particularly when dealing with complex, high-dimensional data? A. Its ability to handle noise and outliers effectively. B. Its robustness to varying densities within the data. C. Its capability to discover clusters of varying shapes and sizes. D. All of the above. Correct. This statement is accurate. HDBSCAN is highly effective at dealing with noise and outliers in data. It achieves this by leveraging its density-based approach, allowing it to disregard noisy points and focus on areas with a higher concentration of data points. This is illustrated in the diagram where the text mentions HDBSCAN effectively identifies and manages noise points within the data, ensuring they do not significantly impact the clustering process. HDBSCAN effectively identifies and manages noise points within the data, ensuring they do not significantly impact the clustering process. Correct. This statement is also correct. HDBSCAN excels at handling datasets with varying densities. It's designed to discover clusters even when their density differs significantly, making it suitable for complex datasets. The diagram's explanation states, it seamlessly adapts to varying densities within the data, leading to more accurate cluster definitions, particularly when dealing with datasets where clusters have different concentrations. It seamlessly adapts to varying densities within the data, leading to more accurate cluster definitions, particularly when dealing with datasets where clusters have different concentrations. Correct. This is another key strength of HDBSCAN. Unlike algorithms constrained to finding spherical or compact clusters, HDBSCAN can discover clusters of various shapes and sizes. This flexibility is crucial when dealing with real-world data often characterized by complex structures. The diagram reinforces this by stating, HDBSCAN can discover clusters of various shapes and sizes. Unlike algorithms limited to spherical or compact cluster forms, HDBSCAN can discover clusters of various shapes and sizes. Unlike algorithms limited to spherical or compact cluster forms. Correct. Given that options A, B, and C are all correct, the statement D, all of the above, is the most accurate answer. HDBSCAN's strengths lie in its ability to handle noise, adapt to density variations, and discover clusters of diverse shapes and sizes, making it a powerful tool for complex data analysis. D. All of the above. Customer segmentation identify distinct groups of customers based on their purchasing behavior or demographics, even with complex interactions and varied spending habits. A company could use HDBS SKlearn to segment its customer base based on their purchasing history and demographics. This could include factors like frequency of purchases, average order value, preferred product categories, age, location, and income. By analyzing this data, the company can identify clusters of customers with similar characteristics, allowing for targeted marketing campaigns and product recommendations. Anomaly detection identify unusual patterns or outliers in data, such as fraudulent transactions or machine failures. By isolating them from the rest of the data points, a bank can utilize HDBS SKlearn to detect fraudulent transactions. By analyzing transaction data, the algorithm can identify outliers that deviate significantly from typical transaction patterns. This could involve analyzing factors like transaction amount, location, time of day, and transaction history. Outliers identified by HDBS SKlearn could then be flagged for further investigation by fraud analysts. Image segmentation divide images into meaningful regions based on color, texture, or other visual features, enabling tasks like object recognition or image analysis. HDBS SKlearn can be used for image segmentation, allowing computers to understand the content of images. For instance, a self-driving car could use HDBS SKlearn to segment the image captured by its camera, identifying objects like roads, lanes, cars, pedestrians, and traffic lights. This segmentation information is crucial for navigation and collision avoidance. Document clustering groups similar documents or articles based on their content, allowing for efficient document organization and information retrieval. HDBS SKlearn can group similar documents together based on their content, enabling more efficient document organization and retrieval. For example, a research library could use HDBS SKlearn to cluster research papers based on their topics and keywords, making it easier for users to find relevant articles. This approach is particularly useful for large collections of documents where manual categorization is impractical. Density-based clustering, a clustering approach that groups data points based on their density or concentration in a feature space. It identifies clusters as regions of high density separated by areas of low density. This approach is well suited for datasets with complex structures, including clusters of varying shapes and sizes. Consider a dataset of customer purchasing data. A density-based clustering algorithm could identify clusters of customers with similar purchasing patterns, even if these patterns are not perfectly spherical or compact. This would enable a company to target its marketing efforts more effectively. DBS SKlearn density-based spatial clustering of applications with noise. A classic density-based algorithm that identifies clusters based on the density of points, effectively separating clusters from noise. It uses two key parameters: min-pt's minimum number of points in a dense region and apes maximum distance between 2 points to be considered neighbors. DBS SKlearn assigns points as core, border, or noise based on their density and neighborhood. Hierarchical density-based clustering, a technique that extends density-based clustering by constructing a hierarchical representation of the clusters, enabling the identification of clusters at different levels of granularity. HDBS SKlearn is an example of this approach. It builds a hierarchical tree structure, allowing analysts to explore clusters at various levels of detail and choose the most appropriate clustering for their analysis. Condensed nearest neighbor CNN graph. A graph structure used by HDBaScan to efficiently represent the relationships between data points, allowing for faster computation of cluster hierarchies. The CNN graph is constructed by selecting a subset of data points that represent the density of A data, creating a more compact representation without losing essential information about the data's structure. Minimum spanning tree MST. A tree structure representing the connections between data points, used by HDBaScan to determine the optimal cluster hierarchy and identify noise points. The MST connects all data points with the shortest possible edges, revealing the underlying connectivity of the data. HDBaScan uses the MST to identify clusters based on the connections between data points, while also identifying points that are poorly connected, indicating noise. Stability score. A metric used by HDBaScan to evaluate the robustness of a cluster, reflecting how likely the cluster remains stable even when small changes are made to the data. A high stability score indicates a cluster that is less likely to change drastically with minor data modifications, suggesting that the cluster represents a real and meaningful structure in the data. A low stability score, on the other hand, suggests that the cluster might be more sensitive to data noise or variations, requiring further investigation. Which of the following statement accurately describes feature agglomeration? A. A dimensionality reduction technique that groups features based on their similarity, reducing the number of features while preserving important information. B. A clustering algorithm that groups data points based on their feature similarity, creating clusters of similar data points. C. A feature engineering technique that creates new features by combining existing features, enhancing the model's performance. D. All of the above. A. A dimensionality reduction technique that groups features based on their similarity, reducing the number of features while preserving important information. True. This statement correctly describes feature agglomeration's role in dimensionality reduction. It combines similar features into a single feature, thereby reducing the dimensionality of the data without losing crucial information. Feature agglomeration is a versatile technique that can be used in different contexts. LTBRGT 1. Dimensionality reduction. It reduces features, making the model faster and preventing the curse of dimensionality. LTBRGT 2. Clustering. It can be used as a pre-processing step before applying clustering algorithms to improve their performance. LTBRGT 3. Feature engineering. By grouping similar features, it can create new, more informative features for the model. B. A clustering algorithm that groups data points based on their feature similarity, creating clusters of similar data points. True. Feature agglomeration can be used as a pre-processing step to improve the performance of clustering algorithms by grouping similar features. It helps the clustering algorithm identify more accurate clusters. Feature agglomeration is a versatile technique that can be used in different contexts. LTBRGT 1. Dimensionality reduction. It reduces features, making the model faster and preventing the curse of dimensionality. LTBRGT 2. Clustering. It can be used as a pre-processing step before applying clustering algorithms to improve their performance. LTBRGT 3. Feature engineering. By grouping similar features, it can create new, more informative features for the model. C. A feature engineering technique that creates new features by combining existing features, enhancing the model's performance. True. This statement is also true. Feature agglomeration can be seen as a form of feature engineering where new, more informative features are created by combining similar existing features. This can lead to improved model performance. Feature agglomeration is a versatile technique that can be used in different contexts. LTBRGT 1. Dimensionality reduction. It reduces features, making the model faster and preventing the curse of dimensionality. LTBRGT 2. Clustering. It can be used as a preprocessing step before applying clustering algorithms to improve their performance. LTBRGT 3. Feature engineering by grouping similar features. It can create new, more informative features for the model. D. All of the above. True. All the preceding statements accurately describe feature agglomeration. It serves as a dimensionality reduction technique, a preprocessing step for clustering, and a feature engineering method, making it a versatile tool in machine learning. Feature agglomeration is a versatile technique that can be used in different contexts. LTBRGT 1. Dimensionality reduction. It reduces features, making the model faster and preventing the curse of dimensionality. LTBRGT 2. Clustering. It can be used as a preprocessing step before applying clustering algorithms to improve their performance. LTBRGT 3. Feature engineering by grouping similar features. It can create new, more informative features for the model. D. All of the above. LT font style font size 14px GT LTBGT dimensionality reduction LT font GT. A technique that reduces the number of features variables in a dataset, while preserving as much relevant information as possible. This is crucial for dealing with the curse of dimensionality, which can lead to model overfitting and computational inefficiency. Imagine you are trying to predict house prices based on 100 different features like square footage, number of bedrooms, location, etc. Using dimensionality reduction, you could reduce these 100 features to maybe 10 or 20 without losing significant information, making the model faster and less prone to overfitting. LT font style font size 12px GT image recognition reducing the number of pixels features in an image without losing important visual information. LT font GT. In image recognition, each pixel in an image represents a feature. By reducing the number of pixels, you can simplify the data without compromising the ability to recognize objects. LT font style font size 12px gene expression analysis identifying groups of genes with similar expression patterns. LT font GT. In gene expression analysis, each gene represents a feature. Dimensionality reduction can help identify groups of genes with similar expression patterns, simplifying the analysis and highlighting key biological pathways. LT font style font size 14px GT LTBGT clustering LTBGT LT font TGT. Unsupervised learning technique where data points are grouped into clusters based on their similarity. Clustering algorithms aim to identify natural groupings in the data, revealing underlying patterns and structures. Suppose you have data on customer purchases. You can use a clustering algorithm to group customers into clusters based on their spending habits, e.g., frequent buyers, occasional buyers, high-value buyers. LT font style font size 12px customer segmentation grouping customers based on their purchasing behavior or demographics. LT font GT. Clustering can help businesses segment their customers into different groups based on their buying patterns. allowing for more targeted marketing campaigns. LT font style font size 14px GT LTBGT feature engineering LTBGT LT font TGT. Process of creating new features from existing ones to improve a model's performance. It involves transforming raw data into features that are more relevant and informative for the learning algorithm. If you have data on customer purchases, you can create a new feature called total purchase amount by adding up all the individual purchase values for each customer. LT font style font size 12px GT text analysis combining similar words or phrases to create more meaningful features for text classification. LT font GT. In text analysis, feature engineering can involve combining similar words or phrases into more meaningful features, improving the accuracy of text classification models. Suppose you are working with a dataset of customer transactions containing features like quotage quote income quote purchase frequency quote average order value quote, etc. You want to cluster customers based on their spending habits. Using feature agglomeration, you can group similar features like income and average order value into a single combined feature, representing the overall spending power. This simplifies the dataset and helps the clustering algorithm focus on the most important aspects of customer spending. From sklearn, cluster import feature agglomeration. From sklearn, datasets import makeblobs. X, Y makeblobs n samples 200. N features 5. Centers 3. Random state 42. UG feature agglomeration clusters 2. X transformed UG. Fit transform X. Printx transformed. Shape. This code demonstrates how to use feature agglomeration in Python using the sklearn library. It first generates a sample dataset with 5 features and 3 clusters. Then, it creates a feature agglomeration object with 2 clusters and applies it to the dataset. The resulting transformed dataset will have only 2 features, effectively reducing the dimensionality of the original data. You are tasked with grouping customers based on their purchase history. Which of the following k-means parameters is crucial for determining the number of customer clusters? A. LT font color code 0000FF code GT init font GT determines the method used to initialize cluster centroids. LT font color code 0000FF quote example LT font GTK means for smarter initialization. B. LT font color code 0000FF quote GTN clusters LT font TGT specifies the desired number of clusters to form. LT font color code 0000FF quote example LT font GTN clusters 3 creates 3 distinct customer clusters. C. LT font color code 0000FF TGT max detailed font GT defines the maximum number of iterations for the k-means algorithm to run. LT font color code 0000FF quote example LT font GT max iter 300 allows for 300 iterations before stopping. D. LT font color code 0000FF TGT random statelt font GT controls the randomness in centroid initialization. LT font color code 0000FF quote example LT font GT random state 42 ensures reproducible results. The init parameter controls how the initial cluster centroids are selected. While it impacts the starting point of the clustering process, it doesn't directly determine the number of clusters. It simply influences the path to the final cluster configuration. False. A. LT font color code 0000FF code GT init font GT determines the method used to initialize cluster centroids. LT font color को 0000FF quote example LT font GTK means for smarter initialization. The N clusters parameter is the cornerstone of k-means. It dictates the number of clusters the algorithm aims to form. The desired outcome of clustering, e.g., grouping customers into 3 segments, is directly determined by this parameter. True. B. LT font color को 0000FF quote GTN clusters LT font EGT specifies the desired number of clusters to form. LT font color को 0000FF quote example LT font GTN clusters 3 creates 3 distinct customer clusters. The maxiter parameter sets a limit on the number of iterations the k-means algorithm can run. It helps prevent the algorithm from running indefinitely if it gets stuck in a loop. It doesn't directly influence the number of clusters. False. C. LT font color को 0000FF quote EGT maxitailed font GT defines the maximum number of iterations for k-means algorithm to run. LT font color को 0000FF quote example LT font GT maxiter 300 allows for 300 iterations before stopping. The random state parameter controls the randomness involved in centroid initialization. It helps ensure that the clustering results are reproducible, especially when using randomized initialization methods. It doesn't dictate the number of clusters. False. D. LT font color को 0000FF quote EGT random statelt font GT controls the randomness in centroid initialization. LT font color को 0000FF quote example LT font GT random state 42 ensures reproducible results. B. LT font color को 0000FF quote GTN clusters LT font EGT specifies the desired number of clusters to form. LT font color को 0000FF quote example LT font GTN clusters 3 creates 3 distinct customer clusters. Customer segmentation. By varying the value of n clusters, we can explore different segmentation strategies. For example, we can group customers into 3 segments: high spenders, moderate spenders, and low spenders. 10, 20, 15, 25, 20, 30, 25, 35, 30, 40, 2. Given the data points above representing purchase history, e.g., items bought and total amount spent, by setting n clusters to k-means would aim to group these customers into 2 distinct clusters based on their purchase patterns. Unsupervised learning. Clustering algorithms. Centroid-based clustering. Elbow method for optimal k. Silhouette score for cluster quality. What are the key characteristics of the bisecting k-means algorithm in scikit-learn sklearn? A. It's a hierarchical clustering method that recursively bisects clusters based on k-means. B. It's a variant of k-means, designed for handling large datasets with a focus on computational efficiency. C. It operates by initially partitioning the data into a large number of clusters, then iteratively merging similar clusters. D. All of the above. Correct. The core principle of bisecting k-means aligns with hierarchical clustering. It starts with one cluster containing all data points and recursively bisects the largest cluster, using k-means with k2. This process creates a hierarchical structure of clusters, similar to dendrograms in hierarchical clustering. Hierarchical clustering. Correct. Bisecting k-means is indeed a variant of k-means, optimized for handling large datasets. It leverages the partitioning strategy of k-means but applies it in a hierarchical fashion to avoid computationally expensive calculations on the entire dataset. This makes it an efficient solution for dealing with large amounts of data. K-means clustering. Correct. Bisecting K-means can be viewed as a merging strategy in a sense. However, its initial partitioning is not into a large number of clusters. Instead, it starts with one cluster and iteratively splits the largest cluster. So, while merging is indirectly involved, it's not the primary mechanism. Large data sets. Correct. All the statements provided in A, B, and C accurately describe the key characteristics of bisecting K-means. Bisecting K-means. D. All of the above. Bisecting K-means is a clustering algorithm in scikit-learn that combines aspects of both hierarchical and K-means clustering, making it efficient for large datasets. It starts with one cluster containing all data points. Then, it repeatedly applies K-means with K2 to the largest cluster, creating two subclusters. This process continues until the desired number of clusters is reached. Bisecting K-means is particularly useful for tasks such as customer segmentation based on purchasing patterns, document clustering to group similar texts, or image analysis to identify groups of visually similar images. Hierarchical clustering is a method of grouping data points into a hierarchy of clusters, forming a tree-like structured dendrogram. It works by iteratively merging or splitting clusters based on their similarity or dissimilarity. Hierarchical clustering is commonly used for analyzing data in a structured way, such as in taxonomy, evolutionary biology, or market research. K-means clustering is a partition-based clustering algorithm that aims to group data points into K clusters, where K is a predefined number of clusters. It works by iteratively assigning data points to the nearest cluster centroid and updating K centroids based on the assigned data points. K-means clustering is widely used in data mining, pattern recognition, and machine learning for tasks such as image compression, customer segmentation, and document classification. Large datasets are characterized by their sheer volume of data points, which can pose challenges for traditional clustering algorithms. Algorithms like bisecting K-means are designed to handle large datasets efficiently by avoiding calculations on the entire dataset at once. Many real-world applications involve large datasets, such as social media data, web traffic logs, or medical records, where computational efficiency is crucial. Computational efficiency refers to the ability of an algorithm to process data quickly and effectively, especially when dealing with large datasets. Algorithms with high computational efficiency are preferred in scenarios where time is a critical factor. For example, in real-time applications like fraud detection, recommendation systems, or online advertising, fast algorithms are essential for timely decision-making. You have a large dataset containing millions of data points. You need to perform K-means clustering but are concerned about the computational time required for processing such a large dataset. Which of the following sklearn clustering algorithms can help you efficiently handle this situation? By processing data in smaller batches. A. K-means. B. DBSCAN. C. Mini-batch K-means. D. Agglomerative clustering. A. K-means. A. K-means is not ideal for large datasets due to its computational complexity. Why other options are incorrect? B. DBSCAN. B. DBSCAN is density-based and works well for datasets with varying densities. Why other options are incorrect? C. Mini-batch K-means. Mini-batch K-means is designed for large datasets where processing the entire dataset in one go is computationally expensive. It works by iteratively clustering small batches of data, which makes it significantly faster than k-means for large datasets. Explanation. D. Agglomerative clustering. D. Agglomerative clustering is a hierarchical clustering algorithm that can be computationally expensive for large datasets. Why other options are incorrect? C. Mini-batch k-means. K-means clustering, a popular partitioning clustering algorithm that aims to group data points into k-clusters based on their proximity to cluster centroids. Image segmentation, customer segmentation, document clustering. Suppose we have 5 data points with 2 features x1, x2. Data points 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Let's assume we want to cluster these points into 2 clusters k2. 1. Randomly initialize 2 centroids. For example, 1, 2 and 5, 6, 2. Calculate the distance between each data point and each centroid. Assign each data point to the cluster with the closest centroid. 3. Recompute the centroids by averaging the data points in each cluster. 4. Repeat steps 2 and 3 until the cluster assignments stabilize or a certain number of iterations is reached. Mini-batch gradient descent. A variant of gradient descent that uses smaller batches of data to update model parameters in each iteration. This can lead to faster convergence and reduced memory requirements. Training deep learning models, optimizing large-scale machine learning models. Mini-batch gradient descent is particularly useful in optimization problems where the dataset is too large to fit in memory. Consider a linear regression model with a large number of data points n. Instead of processing all n data points in one iteration, mini-batch gradient descent divides the data into smaller batches b of size b. Each iteration updates the model parameters using only the data points in the current batch. This reduces the computational burden and memory requirements. The update rule for the model parameters W in each iteration is as follows. WW, LW, XB, YUB. Where is the learning rate? L is the gradient of the loss function L with respect to W. XB is the batch of input features. And YUB is the corresponding batch of target values. Computational complexity. The computational complexity of an algorithm describes the amount of resources, such as time and memory, required to execute the algorithm. Comparing different sorting algorithms, evaluating the efficiency of different search algorithms. Consider sorting a list of numbers. The computational complexity of different sorting algorithms varies. For example, bubble sort has a time complexity of n2, where n is the length of the list. This means the time required to sort the list increases quadratically with the size of the list. On the other hand, merge sort has a time complexity of n log n, which is generally faster for large lists. Streaming data. Streaming data refers to data that arrives continuously over time. Algorithms designed to handle streaming data must be able to process data as it arrives without storing all the data in memory. Real-time fraud detection, traffic analysis, social media sentiment analysis. Imagine a scenario where you are monitoring sensor data coming from a network of devices. The data arrives at a high rate, and you need to detect anomalies in real time. A streaming algorithm can process the data as it arrives, without storing it in memory. For example, you can use a sliding window to analyze a fixed window of recent data points to detect changes in the data stream. Convergence. In optimization algorithms, convergence refers to the process of reaching a stable solution or minimizing the error function. Training machine learning models, Optimizing algorithms. Consider gradient descent optimization. The algorithm iteratively updates model parameters to minimize a loss function. Convergence is achieved when the updates become small enough or the loss function reaches a minimum value. The number of iterations required for convergence depends on various factors, including the learning rate, the complexity of the loss function, and the size of the dataset. Local optimum. A local optimum is a point in the parameter space where the objective function is lower than its neighboring points, but not necessarily the global minimum. Optimization problems. Machine learning training. Imagine a landscape with multiple hills and valleys. A local optimum would be the bottom of a valley, but not necessarily the lowest point in the entire landscape. Gradient descent algorithms can get stuck in local optima if they don't have sufficient mechanisms to escape them. Techniques like momentum, stochastic gradient descent, and simulated annealing can help to mitigate this issue. Which of the following is true about mean shift clustering? A. It requires specifying the number of clusters beforehand. B. It is sensitive to the choice of bandwidth parameter. C. It is particularly well suited for discovering clusters of varying densities. D. All of the above. A. It requires specifying the number of clusters beforehand. False. Mean shift is a density-based clustering algorithm. It does not require specifying the number of clusters beforehand. Instead, it identifies clusters based on the density of data points. This is highlighted in the text. LT font style quote font size 14 px quotient. Mean shift is a density-based clustering algorithm that iteratively moves data points towards areas of higher density. LT font GT. B. It is sensitive to the choice of bandwidth parameter. True. The bandwidth parameter h controls the radius of the search window for density estimation. A well-chosen bandwidth is crucial for accurate clustering. This is explained in the text. LT font style quote font size 14 px quote GT1. Bandwidth parameter h controls the radius of the search window for density estimation. LT font GT. C. It is particularly well suited for discovering clusters of varying densities. True. Mean shift excels in discovering clusters with varying densities. It finds clusters based on density peaks, making it ideal for datasets with non-uniform density distributions. This is highlighted in the text. LT font style quote font size 18 px quote GT LTB GT. Mean shift A. Density-based clustering algorithm LTB GT LT font GT. D. All of the above. True. All the above statements are true about mean shift clustering. The algorithm's reliance on density, sensitivity to bandwidth, and suitability for varying densities make it a powerful clustering technique. This is highlighted in the text. LT font style quote font size 18 px quote GT LTB GT. Correct answer D. All of the above. LTB GT LT font GT. D. A density-based clustering algorithm that iteratively moves data points towards areas of higher density by computing the mean shift vector, which points towards the direction of the highest density increase. LT font style quote font size 18 px quote GT LTB GT. Mean shift a density-based clustering algorithm LTB GT LT font GT. Grouping pixels with similar color characteristics into regions. LT font style quote font size 14 px quote GT1. Image segmentation grouping pixels with similar color characteristics into regions. LT font GT. Identifying customer groups with similar buying patterns. LT font style quote font size 14 px quote GT2. Customer segmentation identifying customer groups with similar buying patterns. LT font GT. Finding outlier data points that deviate from the expected density patterns. LT font style font size 14px GT3. Anomaly detection, finding outlier data points that deviate from the expected density patterns. LT font GT. Identifying moving objects by clustering their positions over time. LT font style font size 14px GT4. Tracking and object detection, identifying moving objects by clustering their positions over time. LT font GT. Controls the radius of the search window for density estimation. A higher bandwidth encompasses more data points, potentially leading to broader clusters. LT font style font size 14px GT1. Bandwidth parameter H controls the radius of the search window for density estimation. LT font GT. Defines the weighing scheme for data points within the search window. Common kernel functions include Gaussian, Epernechnikov, and uniform. LT font style font size 14px GT2. Kernel function defines the weighing scheme for data points within the search window. LT font GT. Calculated as the weighted average of data points within the search window. It represents the direction of the highest density increase from a given data point. LT font style font size 14px GT3. Mean shift vector, calculated as the weighted average of data points within the search window. LT font GT. The iterative process of moving data points along the mean shift vector until convergence to a density peak mode. LT font style font size 14px GT4. Mode seeking, the algorithm iteratively moves data points along the mean shift vector until a convergence point mode is reached. LT font GT. Data points converging to the same mode are grouped together, forming a cluster. LT font style font size 14px GT5. Cluster assignment, data points converging to the same mode are assigned to the same cluster. LT font GT. sklearn. Cluster. Mean shift. The sklearn library provides the mean shift class for implementing mean shift clustering in Python. LT font style font size 16px GT LTBGT sklearn. Cluster. Mean shift LTBGT LT font GT. Mean shift bandwidth none, seeds none, bin seeding false, min freak 1, cluster all true, njobs none. Instantiates a mean shift object. LT font style font size 14px GT. Mean shift bandwidth none, seeds none, bin seeding false, min freak 1, cluster all true, njobs none. Instantiates a mean shift object. LT font GT. Fitx. Fits the model to the data. LT font style font size 14px GT. Fitx fits the model to the data. LT font GT. Predictix. Predicts the cluster labels for new data points. LT font style font size 14px GT. Predictix predicts the cluster labels for new data points. LT font GT. Cluster centers. Returns the coordinates of the cluster centers. LT font style font size 14px GT. Cluster centers returns the coordinates of the cluster centers. LT font GT. Labels. Provides the cluster labels assigned to the data points. LT font style font size 14px GT. Labels provides the cluster labels assigned to the data points. LT font GT. Consider you have a dataset with 1000 data points representing customers of an e-commerce platform. You need to identify distinct customer segments based on their purchase history, browsing behavior, and demographics. Which sklearn clustering technique would be ideal for this task if you suspect nonlinear relationships exist between your customer features? A. K-means clustering. B. DBSCAN. C. Agglomerative clustering. D. Spectral clustering. E. All of the above. A. K-means clustering. K-means clustering is a partitioning-based algorithm that assumes clusters have spherical shapes. This is not ideal for identifying nonlinear relationships, which often result in clusters of irregular shapes. K-means clustering. False. B. DBSCAN. DBSCAN density-based spatial clustering of applications with noise is effective for identifying clusters of varying densities and shapes. It can handle nonlinear relationships to some extent but might struggle with very complex or intertwined clusters. DBSCAN. False. C. Agglomerative clustering. Agglomerative clustering is a hierarchical method that builds clusters by iteratively merging data points. It can handle nonlinear relationships but might be computationally expensive for large datasets and susceptible to noise. Agglomerative clustering. False. D. Spectral clustering. Spectral clustering is a powerful technique well suited for identifying clusters in datasets exhibiting nonlinear relationships. It operates by constructing a graph representation of the data, where nodes represent data points and edges denote their similarity. By analyzing the eigenvalues and eigenvectors of the graph's Laplacian matrix, spectral clustering partitions the data into clusters that are well separated in the graph's spectral space. This approach is particularly effective for identifying complex clusters with irregular shapes or intricate boundaries, making it suitable for scenarios involving customer segmentation where relationships between features can be nonlinear. Spectral clustering. True. E. All of the above. While all the above clustering techniques have their strengths, only spectral clustering is specifically designed to handle nonlinear relationships effectively. K-means. DBSCAN. And agglomerative clustering might struggle to accurately identify complex clusters with intricate shapes and boundaries present in datasets with nonlinear relationships. All of the above. False. D. Spectral clustering. K-means clustering. DBSCAN. Agglomerative clustering. Spectral clustering. Clustering algorithms aim to group similar data points together based on their features. Different algorithms are suitable for specific scenarios depending on the shape of clusters, density, and presence of noise. 1, 1, 1, 2, 2, 1, 2, 2, 5, 5, 5, 6, 6, 5, 6, 6. K-means. 2. Applying K-means with K2 will likely identify two clusters. One around 1, 1 and another around 5, 5. This assumes clusters have spherical shapes and are well separated. Graph representation, Laplacian matrix, eigenvalues and eigenvectors. Graph theory provides a framework to represent relationships between data points using nodes, vertices and edges. Spectral clustering leverages the Laplacian matrix of the graph to analyze the connections and identify clusters. Data points not linearly separable, complex cluster shapes, intricate boundaries. Nonlinear relationships occur when the relationships between features cannot be represented by a straight line. This can lead to clusters with complex shapes and boundaries that traditional linear techniques struggle to identify. Customer segmentation, image segmentation, document clustering. Clustering algorithms have diverse applications. Customer segmentation groups customers with similar traits. Image segmentation identifies objects in images. And document clustering categorizes documents based on content. From sklearn, cluster import spectral clustering. Model spectral clustering N clusters 3. Affinity RBF. Assign labels k-means. Model, fit data. Labels model, labels. Scikit-learn sklearn provides a convenient implementation for spectral clustering. The N clusters parameter specifies the number of desired clusters. Affinity determines the similarity measure used to construct the graph, e.g. RBF for radial basis function. And assign labels sets the method to assign labels to clusters. Which of the following statements accurately describe spectral biclustering in sklearn? A. It uses a spectral decomposition of the data matrix to identify biclusters. B. It aims to find submatrices within the data that exhibit strong row and column coherence. C. It leverages a graph partitioning technique to identify biclusters based on the similarity of rows and columns. D. All of the above. D. All of the above. True. This statement is accurate. Spectral biclustering uses spectral decomposition of the graph Laplacian matrix, which represents the data as a bipartite graph. This decomposition helps identify biclusters, as explained in the explanation block. Explanation. True. This statement is also accurate. Spectral biclustering seeks to discover submatrices where rows and columns show strong correlations, indicating meaningful patterns within the data. This coherence is a key aspect of biclustering, as explained in the explanation block. Explanation. True. This statement is correct. The algorithm utilizes a graph partitioning technique, treating the data as a bipartite graph where nodes represent rows and columns, and edges signify similarities. The partitioning of this graph based on spectral decomposition reveals the biclusters. This is described in the explanation block. Explanation. True. This statement is correct because all the previous choices accurately describe spectral biclustering in sklearn. Choices. Gene expression analysis. Identify groups of genes and samples that exhibit co-regulated patterns. Use cases. Document clustering. Discover sets of documents and keywords that share strong associations. Use cases. Image segmentation. Segment images by identifying regions with similar pixel values. Use cases. Market basket analysis. Uncover sets of products frequently purchased together. Use cases. Spectral clustering. A clustering technique that uses the spectrum eigenvalues and eigenvectors of a similarity matrix to partition data points. Spectral clustering. Graph Laplacian. A matrix that represents the connections in a graph. It's crucial for spectral clustering and biclustering. Graph Laplacian. Eigenvalue decomposition. The process of breaking down a matrix into its eigenvalues and eigenvectors, used to reveal underlying structure in data. Eigenvalue decomposition. Bipartite graph. A graph with two distinct sets of nodes, where connections only exist between nodes from different sets. Bipartite graph. sklearn. Cluster. Spectral biclustering. sklearn. Cluster. Spectral biclustering. Suppose we have a data matrix representing the purchase frequency of 5 products A, B, C, D, A by 4 customers 1, 2, 3, 4, 3, 1, 0, 2, 0, 2, 4, 1, 1, 0, 1, 3, 2, 3, 2, 0, 0, 1, 3, 2. Spectral biclustering would identify submatrices within this data indicating co-purchase patterns. For example, a submatrix might reveal that customers 1 and 4 often purchase products A and D together. Which of the following statements accurately describes the use case of spectral co-clustering in scikit-learn? A. It's best for finding clusters where data points are close together in a high-dimensional space. B. It's ideal for identifying clusters where rows and columns of a data matrix exhibit similar behavior. C. It excels in discovering clusters where data points are well separated in a low-dimensional space. D. It's particularly effective in clustering text data based on word frequencies. A. It's best for finding clusters where data points are close together in a high-dimensional space. Incorrect. Spectral co-clustering focuses on finding clusters based on similar behavior of rows and columns of a data matrix, not just proximity of data points in high-dimensional space. Spectral clustering, similarity matrix, k-means clustering. B. It's ideal for identifying clusters where rows and columns of a data matrix exhibit similar behavior. Correct. Spectral co-clustering excels in identifying clusters where both rows and columns of the data matrix exhibit similar patterns. Co-clustering, spectral clustering. C. It excels in discovering clusters where data points are well separated in a low-dimensional space. Incorrect. While spectral co-clustering can work in low-dimensional space, its core strength is in finding clusters based on row and column similarity, not just spatial separation. Spectral clustering, k-means clustering. D. It's particularly effective in clustering text data based on word frequencies. Incorrect. Spectral co-clustering is a general-purpose method and can be used for text data, but it's not specifically designed for word frequency-based clustering. Document analysis, similarity matrix. B. Simultaneously groups both rows and columns of a data matrix. Imagine a matrix where rows represent customers and columns represent products. Co-clustering would find groups of customers who buy similar products and groups of products that are bought by similar customers. Uses the spectrum of a similarity matrix to find clusters. Consider a dataset of student grades. Spectral clustering could group students based on their performance in different subjects. Analyzing the relationships between students and subject areas represents the connectivity of a graph, used in spectral clustering. In a social network graph, the Laplacian matrix would show connections between individuals. Spectral clustering would then identify communities within this network based on these connections. Used to identify the clusters in spectral clustering. By analyzing the eigenvalues and eigenvectors of the Laplacian matrix, spectral clustering identifies the most significant connections and groupings within the data. Used as a post-processing step in spectral clustering. After spectral clustering assigns initial cluster assignments, k-means can refine these assignments by moving data points closer to cluster centers. Enhancing the clustering result represents the pairwise similarity between data points. Imagine a matrix representing the similarity of different movie genres. Spectral clustering would then find clusters of genres that share similar characteristics. An alternative clustering algorithm. Affinity propagation can be used to find clusters in datasets where the number of clusters is not known beforehand. This is helpful for datasets with complex structures. Density-based clustering algorithm. DBSCAN can effectively identify clusters in datasets with varying densities. It is useful for finding clusters with irregular shapes and handling outliers. From sklearn, cluster import spectral co-clustering. Co-cluster spectral co-clustering n clusters 5. 4. Random state 42. Co-cluster, fit data. Row labels co-cluster, row labels. Column labels co-cluster, column labels. Which of the following statements are true about the affinity propagation clustering algorithm in scikit-learn? A. It is a deterministic algorithm, meaning that it always produces the same clusters given the same data. B. It is a distance-based clustering method, requiring a distance metric to calculate cluster similarity. C. It automatically determines the optimal number of clusters based on the data. D. It requires a predefined number of clusters as input. E. All of the above. A. It is a deterministic algorithm, meaning that it always produces the same clusters given the same data. Correct affinity propagation, while iterative, uses a fixed set of parameters and calculations, resulting in consistent cluster formation for the same input data. Therefore, it's considered deterministic. A. It is a deterministic algorithm, meaning that it always produces the same clusters given the same data. B. It is a distance-based clustering method, requiring a distance metric to calculate cluster similarity. Correct affinity propagation works by calculating the similarity or dissimilarity between data points. This requires a distance metric to quantify the relationship between data points. B. It is a distance-based clustering method, requiring a distance metric to calculate cluster similarity. C. It automatically determines the optimal number of clusters based on the data. Correct affinity propagation avoids predefining the number of clusters. It dynamically finds the optimal number of clusters by examining the data's structure in relationships. C. It automatically determines the optimal number of clusters based on the data. D. It requires a predefined number of clusters as input. Incorrect. This statement is the opposite of how affinity propagation works. It doesn't need a predefined number of clusters, unlike methods like k-means. D. It requires a predefined number of clusters as input. E. All of the above. Correct as options A, B, and C are all true. This statement correctly summarizes the characteristics of affinity propagation clustering. E. All of the above. E. All of the above. Unsupervised machine learning technique to group similar data points together. Imagine you have a dataset of customer purchase history. Using clustering, you can group customers with similar buying habits into segments, which could be used for targeted marketing campaigns. Clustering. Clustering algorithm based on message passing between data points to find exemplars cluster centers. Imagine you have a dataset of images of different flowers. Affinity propagation can automatically group images with similar features, e.g., color, shape, into clusters, helping you identify different flower types. Affinity propagation represents the pairwise similarity or dissimilarity between data points. Imagine you have data points representing different cities. The similarity matrix would show the distance between each pair of cities. This matrix is used in affinity propagation to determine the relationships between data points. Similarity matrix. Python library for machine learning, including the affinity propagation clustering algorithm. In Python, using scikit-learn's affinity propagation function, you can apply affinity propagation to your dataset, which could be customer data, image pixels, or text documents. Scikit-learn. Customer segmentation, identifying groups of customers with similar purchasing behavior. You could use affinity propagation to group customers based on their purchase history, product preferences, or spending patterns. This could help you develop more targeted marketing strategies. Customer segmentation, identifying groups of customers with similar purchasing behavior. Image segmentation, grouping pixels in an image based on their color and texture. You could use affinity propagation to segment an image into different regions based on a similarity of color and texture of the pixels. This could be useful for tasks like object recognition or image editing. Image segmentation, grouping pixels in an image based on their color and texture. Document clustering, grouping documents based on their content similarity. You could use affinity propagation to cluster a collection of documents based on their content, such as keywords, topics, or style. This could be useful for organizing documents, identifying related topics, or building a search engine. Document clustering, grouping documents based on their content similarity. Question: which of the following options is not a parameter for the sklearn cluster OPTICSDBSCAN clustering algorithm? A. Min samples. B. Apes. C. Min cluster size. D. Metric. E. All of the above. Min samples. Correct. Min samples is a key parameter for optics DBSCAN. It determines the minimum number of data points required within a neighborhood for a point to be considered a core point. Core points are essential for defining clusters in density-based algorithms. True. Apes. Correct. Apes epsilon is another crucial parameter in OPTICSDBSCAN. It specifies the maximum distance between 2 points for them to be considered neighbors. The value of apes directly impacts the size and shape of clusters. True. Min cluster size. Correct. Min cluster size is also a parameter used in OPTICSDBSCAN. It sets the minimum number of data points required to form a valid cluster. This parameter helps filter out small, insignificant clusters that may arise due to noise. True. Metric. Correct. Metric is a parameter in OPTICSDBSCAN that defines the distance metric used to calculate the distance between data points. Selecting the appropriate metric, e.g., Euclidean distance, Manhattan distance, cosine similarity, is essential for capturing meaningful relationships in the data. True. All of the above. Correct. Since all the options A, B, C, and D are valid parameters for optics DBSCAN, the answer is A. All of the above. True. A. Clustering algorithms are essential tools for grouping similar data points together into clusters based on their characteristics. Different clustering algorithms employ various approaches to achieve this goal. For example, DBSCAN and optics are density-based algorithms that identify clusters based on the density of data points in a given space. Customer segmentation, grouping customers with similar purchasing habits or demographics for targeted marketing campaigns. Anomaly detection, identifying unusual data points that deviate significantly from the normal patterns. Image segmentation, dividing an image into distinct regions based on similar pixel characteristics, such as color or texture. DBSCAN, density-based spatial clustering of applications with noise, is a density-based clustering algorithm that groups data points together based on their density. It identifies clusters as areas of high data density and labels points with low density as noise or outliers. Customer segmentation, identifying groups of customers with high purchasing activity and separating them from less active customers. Anomaly detection, identifying fraudulent transactions in financial data by detecting outliers in transaction patterns. Geographic data analysis, identifying clusters of densely populated areas on a map. Optics ordering points to identify the clustering structure is another density-based clustering algorithm that builds upon DBSCAN. It creates an ordered representation of clusters by finding the most representative points in a Data. This allows for visualizing the cluster structure and exploring different cluster resolutions. Customer segmentation, analyzing the hierarchy of customer segments based on their purchase history and behavior. Anomaly detection, visualizing the evolution of anomalies in a data set over time. Biological data analysis, identifying clusters of genes with similar expression patterns. Optics DBSCAN combines the strengths of both DBSCAN and optics to provide a robust and versatile clustering solution. It can identify clusters of various shapes and sizes while effectively handling noise and outliers. Customer segmentation, creating a detailed and accurate segmentation of customers based on their purchasing behavior and demographics. Anomaly detection, identifying both isolated outliers and clusters of anomalies in a dataset. Image segmentation, segmenting images with complex structures and variations in density. Distance metrics play a crucial role in clustering algorithms by measuring the similarity between data points. Different distance metrics capture different types of relationships between data points. Euclidean distance calculates the straight line distance between two points in a multidimensional space. Manhattan distance calculates the distance between two points by summing the absolute differences of their coordinates. Cosine similarity measures the angle between two vectors, representing the similarity between them. Clustering algorithms have numerous applications across various domains, including customer segmentation, anomaly detection, and image segmentation. Customer segmentation, grouping customers with similar purchasing habits or demographics for targeted marketing campaigns. Anomaly detection, identifying unusual data points that deviate significantly from the normal patterns. Image segmentation, dividing an image into distinct regions based on similar pixel characteristics, such as color or texture. The sklearn cluster optics DBSCAN class in the scikit-learn library implements the OPTICS DBSCAN algorithm, providing a convenient and powerful tool for clustering data. It offers various parameters and options for customization, allowing you to fine-tune the clustering process based on your specific data and requirements. Customer segmentation, segmenting customers based on their purchasing behavior, demographics, and other relevant factors. Anomaly detection, identifying unusual transactions or events in financial data, network traffic, or sensor data. Image segmentation, segmenting images into different regions based on color, texture, or other pixel characteristics. What are the possible uses of cluster optics XI method of sklearn cluster module? A. Finding clusters of varying densities and shapes. B. Detecting clusters with different sizes and dimensions. C. Identifying outliers in the dataset. D. All of the above. Solution. True. The cluster optics XI method implements optics clustering, a density-based clustering algorithm that excels at identifying clusters with diverse densities and forms. It considers the distribution of data points, effectively grouping those with higher density and distinguishing clusters with irregular shapes. Solution. True. Optics clustering is capable of recognizing clusters with varying sizes and dimensions. It adapts to data structures with different scales and feature spaces, allowing it to identify both small, concentrated clusters and large, spread out clusters. Solution. True. Due to its density-based nature, optics clustering can effectively detect outliers. Outliers are points that are sparsely distributed and do not belong to any dense cluster. Optics identifies these points as anomalies within the data. Answer. True. Considering the explanations above, Choice D correctly encapsulates the capabilities of cluster optics Xi in handling clusters of varying densities and shapes, identifying clusters with different sizes and dimensions, and effectively detecting outliers. D. All of the above. Related concepts. The cluster optics Xi method is a specific implementation of optics clustering within a sklearn cluster module in Python. It offers a powerful tool for density-based clustering. Related concepts. The sklearn cluster module in Python provides a collection of clustering algorithms, including cluster optics Xi. It serves as a comprehensive library for applying various clustering techniques. Related concepts. Optics ordering points to identify the clustering structure is a density-based clustering algorithm that excels at identifying clusters of varying densities and shapes. It expands upon DBSCAN's capabilities by capturing the cluster hierarchy within the data. Related concepts. Density-based clustering algorithms, like optics and DBSCAN, group data points based on their density. They identify clusters as areas of high density separated by regions of low density, making them suitable for handling irregularly shaped clusters. Related concepts. Outlier detection refers to the process of identifying data points that deviate significantly from the general pattern of the data. These outliers may represent errors, anomalies, or unique instances that require further investigation. Use cases. In network security, optics clustering can be applied to detect anomalies in network traffic patterns. By analyzing the density of network activity, unusual patterns indicating potential attacks or intrusions can be identified. Use cases. Optics clustering is useful for segmenting customers based on their purchase behavior and transaction frequency. By grouping customers with similar purchase patterns, businesses can tailor marketing strategies and offers more effectively. Use cases. In image processing, optics clustering can be used to segment images based on the density and spatial distribution of pixels. This enables the identification of objects and regions within an image, facilitating analysis and interpretation. What does the LT font color (blue) compute optics graph LT font EGT method in scikit-learn's optics clustering algorithm calculate? A. The reachability distances between all points in the dataset. B. The density-based clustering hierarchy based on reachability distances. C. The coedistances for each data point. D. All of the above. A. The reachability distances between all points in the dataset. Correct. Reachability distance is a key concept in optics, representing the distance from a point to a cluster based on its nearest neighbor within that cluster. The compute optics graph method calculates these distances for all points in the dataset. True. B. The density-based clustering hierarchy based on reachability distances. Correct. Optics constructs a hierarchical clustering structure based on reachability distances. This structure reveals the relationships between different clusters and how they merge or split at different density levels. True. C. The coedistances for each data point. Correct. Coedistance is another crucial element in optics. It's the minimum distance required for a point to be considered a core point, influencing the density estimation and cluster identification process. True. D. All of the above. Correct. The compute optics graph method calculates all of the above reachability distances, the density-based clustering hierarchy, and coedistances. This information is then used to construct the graph representation of the optics results. True. D. All of the above. Optics ordering points to identify the clustering structure, a density-based clustering algorithm that extends DBSCAN. It overcomes DBSCAN's limitations by finding a hierarchical structure of clusters rather than just flat clusters. Imagine analyzing customer data to segment them into different groups based on their spending habits. Optics can identify not only individual customer segments but also how these segments merge or split at different spending thresholds, providing a more nuanced understanding of customer behavior. Reachability distance: the distance from a data point to a cluster based on its nearest neighbor within the cluster. It helps identify the hierarchical relationships between points and clusters. Consider a set of points representing cities on a map. The reachability distance of a city to a cluster of cities would reflect how easily accessible it is to other cities within the cluster, revealing potential groupings based on proximity and connectivity. Core distance: the minimum distance required for a point to be considered a core point. It's used to determine the density of a region and identify clusters. In a dataset of financial transactions, core distance could be used to identify clusters of high-value transactions. Points with a high core distance would indicate significant spending activity, helping detect potential fraud or unusual spending patterns. Customer segmentation: identify distinct customer groups based on their purchasing patterns, demographics, and other factors to tailor marketing strategies. A retail company could use optics to segment its customer base into groups based on their purchase frequency, average order value, and product categories. This segmentation would help them design targeted marketing campaigns and promotions. Anomaly detection: find unusual data points or patterns that deviate from the expected behavior in datasets like network traffic, financial transactions, or sensor readings. A network security system could use optics to detect unusual traffic patterns or network intrusions. Points that deviate significantly from the typical behavior could indicate malicious activity or anomalies that require further investigation. Image segmentation: divide images into meaningful regions based on pixel similarity, enabling tasks like object recognition and image analysis. In medical imaging, optics could be used to segment brain scans, identifying different regions and structures based on pixel intensity and spatial relationships. This segmentation would aid in disease diagnosis and treatment planning. Which of the following is not a parameter of DBSCAN clustering algorithm? A. Apes. B. Min samples. C. N clusters. D. Metric. Apes. Apes is a parameter of DBSCAN. It defines the maximum distance between 2 points to be considered neighbors. A higher apes value means points can be farther apart to be considered neighbors, leading to larger clusters. False. Min samples. Min samples is another important parameter of DBSCAN. It specifies the minimum number of points required to form a dense region. A higher min samples value means a denser region is needed for a cluster to be formed. False. N clusters. N clusters is not a parameter of DBSCAN. DBSCAN is an unsupervised learning algorithm that does not require the number of clusters to be specified beforehand. It automatically identifies clusters based on density. True. Metric. Metric is a parameter of DBSCAN. It defines the distance metric used to calculate neighborhood. Common metrics include Euclidean distance, Manhattan distance, etc. Choosing the right metric depends on the nature of the data. False. C. N clusters. DBSCAN. DBSCAN stands for density-based spatial clustering of applications with noise. It's a powerful clustering algorithm that groups data points based on their density. It's particularly effective at identifying clusters of varying shapes and sizes, as well as outliers. Apes. Apes represents the maximum radius of the neighborhood around a data point. Points within this radius are considered neighbors. It's a crucial parameter that determines the size and shape of the clusters. A higher ape's value results in larger clusters and may merge smaller clusters together. Min-samples. Min-samples defines the minimum number of data points required to form a dense region. A high min-samples value implies a denser region is needed to be considered a cluster. This parameter helps to avoid the identification of small, isolated clusters. Metric. The metric parameter specifies how the distance between data points is calculated. Common metrics include Euclidean distance, Manhattan distance, and cosine similarity. The choice of metric depends on the nature of the data and the distance measure most relevant to the task. Outlier detection. DBSCAN can effectively identify outliers, which are data points that are significantly different from other points in the dataset. This is particularly useful in anomaly detection, fraud detection, and identifying unusual patterns in data. Image segmentation. DBSCAN can be applied to segment images by grouping pixels based on their color, texture, or other features. It can identify objects or regions in an image, providing valuable insights for image analysis and object recognition. Customer segmentation. DBSCAN can segment customers into groups based on their purchasing behavior, demographics, or other characteristics. This allows businesses to target their marketing campaigns more effectively and provide personalized services based on customer segments. Let's consider a dataset of 10 data points with two dimensions x, y, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 7, 8, 8, 9, 9, 10, 11, 12, 12, 13. We want to apply DBSCAN with apes2 and minsamples 3. Neighborhood. A data point is considered a neighbor to another point if the distance between them is less than or equal to apes2 in this case. For example, 1, 2 and 2, 3 are neighbors, while 1, 2 and 7, 8 are not. Copoint. A point is considered a copoint if it has at least minsamples 3 in this case. Neighbors within a radius of apes2 in this case. So, 2, 3 is a copoint because it has neighbors 1, 2 and 3. 4 within a radius of 2, 1, 2 is not a copoint because it has only one neighbor 2. 3 within a radius of 2. Border point. A point is considered a border point if it is not a copoint but has at least one copoint as a neighbor. For example, 1, 2 is a border point because it has a copoint 2. 3 is a neighbor. Noise point. A point is considered a noise point if it is neither a copoint nor a border point. In this example, 7, 8 and 8, 9 are noise points. Cluster. A cluster is formed by connecting all copoints and border points that are reachable from each other. In this example, data points 1, 2, 2, 3, 3, 4, 4, 5, 5, 6 will form one cluster, and data points 9, 10, 11, 12, 12, 13 will form another cluster. The noise points will not be part of any cluster. What does the estimate bandwidth function in sklearn do? A estimates the optimal bandwidth for DBSCAN using the k-nearest neighbors algorithm. B determines the best number of clusters for k-means clustering by finding the elbow point in k. Inertia plot. C. Calculates the silhouette score for a given clustering algorithm. D. All of the above. Estimates the optimal bandwidth for DBSCAN using the k-nearest neighbors algorithm. True. This statement is correct. The estimate bandwidth function in scikit-learn specifically targets DBSCAN clustering. It employs the k-nearest neighbors algorithm to identify the optimal value for the apes parameter in DBSCAN. This apes value represents the maximum distance between 2 points to be considered neighbors. DBSCAN clustering determines the best number of clusters for k-means clustering by finding the elbow point in k. Inertia plot. False. This statement is incorrect. The estimate bandwidth function doesn't deal with k-means clustering. The process of finding the elbow point in the inertia plot is a technique used for estimating k. Optimal number of clusters within k-means clustering, but not directly related to estimate bandwidth. K-means clustering calculates the silhouette score for a given clustering algorithm. False. This statement is incorrect. The estimate bandwidth function doesn't compute the silhouette score. The silhouette score is a metric used to evaluate the quality of a clustering result. It assesses how well each point fits within its cluster compared to other clusters. Silhouette score. All of the above. False. This statement is incorrect. As explained earlier, the estimate bandwidth function is specifically for DBSCAN and doesn't encompass the other functionalities mentioned in the choices. Now, A. Density-based spatial clustering of applications with noise. DBSCAN is an algorithm used to identify clusters of high density in data, separating noise from those clusters. Outlier detection, image segmentation, customer segmentation, anomaly detection in sensor data. In DBSCAN, the apes parameter represents the maximum distance between 2 points to be considered neighbors. Defining the neighborhood size for DBSCAN clustering. The k-nearest neighbors KNN algorithm is a non-parametric method used for classification and regression. It identifies the k-nearest data points to a given point based on a distance metric. Estimating the optimal bandwidth for DBSCAN. Classification, regression, recommendation systems. The silhouette score is a metric used to evaluate the quality of a clustering result. It measures how well each point fits within its cluster compared to other clusters. Evaluating the performance of different clustering algorithms. Determining the optimal number of clusters. The elbow method is a technique used to determine the optimal number of clusters in k-means clustering. It involves plotting the within-cluster sum of squares inertia against the number of clusters and observing the point where the rate of decrease in inertia starts to slow down, forming an elbow. Estimating the optimal number of clusters for k-means clustering. K-nearest neighbors. Let's say we have 5 data points in a 2-dimensional space, represented by their coordinates A1, 2, B3, 1, C4, 3, D2, 4, and E5, 2. We want to find the 3 nearest neighbors of point A1, 2 using the Euclidean distance. Calculating the Euclidean distances between A and the other points. Distance A, B sqrt 3, 1 2, 1, 2 2 sqrt 5. Distance A, C sqrt 4, 1 2, 3, 2 2 sqrt 10. Distance A, D sqrt 2, 1 2, 4, 2 2 sqrt 5. Distance A sqrt 5, 1 2, 2, 2 2 sqrt 16. The 3 nearest neighbors of A are B, D, and A itself, as they have the shortest distances. Which of the following best describes the primary goal of the k-means clustering algorithm? A. To identify the optimal number of clusters in a dataset. B. To find the most similar data points within a dataset. C. To partition data points into k distinct clusters based on their similarity. D. To determine the most influential data points in a dataset. E. All of the above. While identifying the optimal number of clusters is important, it's not the primary goal of the k-means algorithm itself. The algorithm assumes the number of clusters k is predefined. Determining the optimal k typically involves techniques like the elbow method. False. The elbow method is a technique used to find the optimal number of clusters k in a dataset. It involves plotting the inertia values for different values of k and looking for an elbow point in the plot, where the rate of decrease in inertia slows down significantly. K-means aims to group similar data points together, but it doesn't specifically focus on finding the most similar pairs within the entire dataset. Its goal is to partition the data into clusters based on overall similarity. False. Clustering is the task of grouping a set of objects in such a way that objects in the same group cluster are more similar to each other than to those in other groups. This is the core principle of the k-means algorithm. It partitions data points into k clusters, aiming to minimize the distance between points within each cluster, thereby maximizing similarity within clusters. True. The k-means algorithm works by partitioning data points into LTBGT distinct clusters, where LTBGT is a user-defined parameter representing the number of desired clusters. The goal is to group similar data points together while minimizing the distance between data points within the same cluster. K-means is not designed to identify influential data points. It focuses on partitioning data into clusters based on similarity, not influence. False. Centroids represent the mean or average of all data points within a cluster. They are used as reference points for cluster assignments. Since options A, B, and D are incorrect, A cannot be the correct answer. False. The k-means algorithm works by partitioning data points into LTBGT distinct clusters, where LTBGT is a user-defined parameter representing the number of desired clusters. The goal is to group similar data points together while minimizing the distance between data points within the same cluster. C. To partition data points into k distinct clusters based on their similarity. The process of grouping similar objects together in k-means. It's about grouping data points based on their features. Customer segmentation based on purchasing behavior, demographics, etc. Document clustering to organize information into meaningful topics. Image compression by grouping similar pixels. Imagine you have data about students' scores in math and science. You can cluster them into groups based on their performance in both subjects. Students with high scores in both subjects would form one cluster, while students with low scores in both would form another. The central point representing a cluster in k-means. It's the average of all data points within a cluster, representing the average customer profile within a customer segment, determining the center of a cluster of documents with similar content. If you have 3 data points with coordinates 1, 2, 3, 4, and 5, 6, their centroid would be 3, 4 the average of the x and y coordinates. Functions that quantify the similarity or dissimilarity between data points. Commonly used metrics include Euclidean distance, Manhattan distance, and cosine similarity, calculating the distance between two customer profiles based on their purchase history. Determining the similarity between two documents based on their word vectors. The Euclidean distance between points 1, 2 and 3, 4 is calculated as 3, 1, 4, 2, which is 22. A metric to evaluate the quality of clustering. It's the sum of squared distances between each data point and its assigned cluster centroid. Lower inertia generally indicates better clustering. Comparing different clustering algorithms based on their inertia scores. Evaluating the effectiveness of different feature sets in achieving better clustering. Imagine you have two clusters with centroids 2, 3 and 5, 6. Data point 1, 2 is assigned to the first cluster. Its squared distance to the centroid is 1, 2, 2, 3. Which is 2. Summing up such squared distances for all data points gives you the inertia. A technique for finding the optimal number of clusters k by plotting inertia values for different values of k. The elbow point, where the rate of inertia decrease slows down, suggests the optimal k, determining the best number of customer segments for a targeted marketing campaign. Choosing the optimal number of topics for document clustering based on the content. You calculate inertia for different values of k, e.g. 2, 3, 4, 5. When plotted, you might observe a sharp drop in inertia from k2 to k3, but a less significant drop from k3 to k4. The elbow might be around k3. Suggesting that 3 is the optimal number of clusters. Which of the following statements is true about the mean shift clustering algorithm? It requires the user to specify the number of clusters in advance. It uses a distance metric to determine cluster centers. It is sensitive to the choice of bandwidth parameter. All of the above. It requires the user to specify the number of clusters in advance. This statement is false. Mean shift clustering is a non-parametric algorithm, which means it does not require prior knowledge about the number of clusters. It discovers the clusters based on the data density. Non-parametric. It uses a distance metric to determine cluster centers. This statement is true. Mean shift uses a distance metric to calculate the density gradient, which helps it identify regions of high density representing cluster centers. Distance metric. It is sensitive to the choice of bandwidth parameter. This statement is true. The bandwidth parameter controls the size of the neighborhoods around data points. A larger bandwidth results in smoother density estimations and fewer clusters, while a smaller bandwidth may lead to oversegmentation and a larger number of clusters. Bandwidth. All of the above. This statement is true. As explained above, statements A, B, and C are either true or false. Therefore, all of the above is also true. Mean shift. D. Clustering. Clustering is an unsupervised learning technique used to group similar data points together based on their features. It aims to discover patterns and structures in data without any prior labeling. In customer segmentation, clustering can be used to group customers based on their purchasing behavior, demographics, or other relevant factors, allowing businesses to tailor marketing campaigns and provide personalized experiences. Mean shift. Mean shift is a non-parametric clustering algorithm that uses a density gradient to find cluster centers. It iteratively shifts data points towards regions of higher density until convergence. In image segmentation, mean shift can be used to group pixels with similar colors into distinct regions, making it useful for tasks like object detection and scene understanding. Bandwidth. Bandwidth is a parameter in mean shift that determines the size of the neighborhoods around data points. It controls the smoothness of the density estimation and influences the number of clusters found. In object tracking, choosing the right bandwidth can help track objects more effectively. A larger bandwidth can handle more noise and variation in the object's appearance, while a smaller bandwidth might lead to better detail but could be more sensitive to noise. Distance metric. A distance metric is used in mean shift to measure the similarity between data points. Common metrics include Euclidean distance, Manhattan distance, and cosine similarity. In anomaly detection, choosing a suitable distance metric is crucial. For example, using Euclidean distance might work well for detecting anomalies in numerical data, while cosine similarity is suitable for detecting anomalies in text or image data. Non-parametric. Non-parametric methods do not assume a specific underlying distribution for the data. This allows mean shift to adapt to complex data structures without predefined assumptions. In customer segmentation, non-parametric methods are useful when the customer data is diverse and does not fit a predefined distribution. This allows for a more flexible and accurate segmentation based on the actual data characteristics. Which of the following statements are true about scikit-learn's spectral clustering algorithm? A. It constructs a similarity graph based on the data and then applies a spectral decomposition to find clusters. B. It uses the eigenvectors of the Laplacian matrix to find cluster assignments. C. It is particularly effective for handling non-linearly separable data. D. All of the above. A. It constructs a similarity graph based on the data and then applies a spectral decomposition to find clusters. This statement is correct. Spectral clustering begins by constructing a similarity graph where nodes represent data points and edges represent the similarity between them. The strength of the connection between nodes is determined by the chosen distance metric, e.g., Euclidean distance, Gaussian kernel. This graph representation captures the underlying data structure. Subsequently, the algorithm performs a spectral decomposition on the graph's Laplacian matrix, revealing information about the graph structure, specifically how data points are interconnected. Constructing a similarity graph spectral decomposition. Spectral clustering, as implemented in scikit-learn's spectral clustering function, leverages a graph-based approach to cluster data. B. It uses the eigenvectors of the Laplacian matrix to find cluster assignments. This statement is also correct. After the spectral decomposition, the algorithm uses the eigenvectors of the Laplacian matrix to find cluster assignments. The eigenvectors encode information about the connectivity of the graph. Typically, k-means clustering is applied to the eigenvectors where k represents the desired number of clusters. To determine which data points belong to which cluster. Eigenvalues and eigenvectors, clustering assignment. Finally, the eigenvectors are used to assign data points to clusters. Typically, k-means clustering is applied to the eigenvectors with k being the desired number of clusters. C. It is particularly effective for handling non-linearly separable data. This statement is also correct. Spectral clustering excels in handling non-linearly separable data. Traditional methods like k-means might struggle in such scenarios, as they rely on Euclidean distance, which is sensitive to the shape of the data. However, spectral clustering uses the graph representation to capture complex relationships and identify clusters even when they are not linearly separated. Similarity graph. Spectral clustering, as implemented in scikit-learn's spectral clustering function, leverages a graph-based approach to cluster data. D. All of the above. This statement is correct since all the previous statements are true about the spectral clustering algorithm. All concepts. All. D. All of the above. Identifying regions of interest in an image, like separating foreground from background. Finding groups of people who are tightly connected within a social network. Grouping similar documents based on their content. Categorizing customers into groups based on their buying behavior. 1, 1, 1, 2, 2, 2, 3, 3, 4, 4, 5, 5, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, minus 1, 0, 0, 0, 0, minus 1, 2, minus 1, 0, 0, 0, 0, minus 1, 2, minus 1, 0, 0, 0, 0, minus 1, 2, minus 1, 0, 0, 0, 0, minus 1, 2, minus 1, 0, 0, 0, 0, minus 1, 1, minus 0.267, minus 0.534, minus 0.6, minus 0.534, minus 0.267, 0, 0.447, 0.289, minus 0.089, minus 0.289, minus 0.447, 0, minus 0.447, minus 0.289, 0.089, 0.289, 0.447, 0, 0.447, 0.289, minus 0.089, minus 0.289, minus 0.447, 0, minus 0.267, minus 0.534, minus 0.6, minus 0.534, minus 0.267, 0, 0, 0, 0, 0, 0, 1. Which of the following statements accurately describe the purpose and functionality of the war tree? In scikit-learn's hierarchical clustering, A. It constructs a hierarchical tree structure representing the relationships between data points, where each node represents a cluster, and the height of the node indicates the distance between clusters. Correct. Hierarchical tree structure. War tree constructs a hierarchical tree dendrogram that visually represents the relationships between data points. Each node in the tree represents a cluster, and the height of a node indicates the distance between the clusters that are merged to form it. A. Hierarchical tree structure. War tree constructs a hierarchical tree dendrogram that visually represents the relationships between data points. Each node in the tree represents a cluster, and the height of a node indicates the distance between the clusters that are merged to form it. B. It uses a divisive approach, starting with a single cluster and iteratively dividing it based on the greatest distance between points. Correct. Agglomerative approach. The war tree uses an agglomerative approach, starting with individual data points as separate clusters and iteratively merging the closest clusters based on a distance metric. This process is visualized as building the dendrogram from the bottom up. B. Agglomerative approach. The war tree uses an agglomerative approach, starting with individual data points as separate clusters and iteratively merging the closest clusters based on a distance metric. This process is visualized as building the dendrogram from the bottom up. C. It implements the Ward's minimum variance method, aiming to minimize the variance within clusters as they merge, resulting in a dendrogram that reflects this optimization. Correct. Ward's minimum variance method. WARD-tree implements the Ward's minimum variance method, which is a key aspect of its functionality. In Ward's method, the distance between clusters is measured as the increase in variance that occurs when two clusters are merged. The algorithm seeks to minimize this increase in variance during the merging process, resulting in clusters that are internally cohesive low variance and well separated high variance between clusters. C. Ward's minimum variance method. WARD-tree implements the Ward's minimum variance method, which is a key aspect of its functionality. In Ward's method, the distance between clusters is measured as the increase in variance that occurs when two clusters are merged. The algorithm seeks to minimize this increase in variance during the merging process, resulting in clusters that are internally cohesive low variance and well separated high variance between clusters. D. All of the above. Correct. All of the above. All the statements A, B, and C correctly describe the purpose and functionality of the WARD-tree in scikit-learn's hierarchical clustering. The WARD-tree in scikit-learn's hierarchical clustering is indeed a powerful tool for uncovering underlying relationships between data points. Here's a detailed breakdown of its features and how they tie into the answer choices. Hierarchical clustering, a method of grouping data points into a hierarchy of clusters, where clusters are nested within each other. This creates a tree-like structure called a dendrogram. Dendrogram, a tree-like diagram that visually represents the hierarchical relationships between clusters in hierarchical clustering. The height of the branches in the dendrogram indicates the distance between clusters. Agglomerative clustering, a bottom-up approach to hierarchical clustering, where individual data points are initially treated as separate clusters and then progressively merged based on their similarity. Ward's method, a specific linkage criteria used in agglomerative hierarchical clustering that aims to minimize the variance within clusters as they are merged. It considers the increase in variance when merging two clusters and seeks to minimize this increase. Distance metric, a function that measures the dissimilarity between two data points. Different distance metrics can be used depending on the type of data and the desired clustering behavior. Variance, a statistical measure of how spread out a set of data points is. In Ward's method, variance is used to assess the similarity of clusters by measuring the increase in variance when they are merged. Linkage criteria, the rule used to determine the distance between clusters in agglomerative hierarchical clustering. Different linkage criteria lead to different clustering outcomes. Customer segmentation, using hierarchical clustering to group customers based on their purchasing history, demographics, or other relevant factors. This enables businesses to tailor marketing campaigns and offers to specific customer segments. Document clustering, organizing a collection of text documents into meaningful categories based on their content. This helps with information retrieval, topic modeling, and text analysis. Image segmentation, identifying distinct regions or objects within an image by clustering pixels with similar characteristics. This is used in image recognition, object detection, and medical imaging analysis.